So this problem is on the study of heat transfer by conduction. We are given in the figure below a wall consisting of 4 different layers, and we are given the thermal conductivities of 3 of the layers, whereas the thermal conductivity of layer 2 is not known. And we're given the layer thicknesses except for the thickness of layer 2 as well. And we're given some of the temperatures. We have the temperature T1 to be 30, T4 to be -10, and we are given the temperature at the interface T12. We're given that the energy transfer through the wall is steady, and we want to find the interface temperature T34. So basically, you can see that, first of all, the given temperatures T1 and T4, these represent the temperatures at the edges, and these are what we usually label as T cold and T hot. And this is obviously, this is T hot here. And this is T cold. We want the temperature at the interface T34, which is right here. And the expression energy transfer through the wall is steady. This is our key to solving this question, because we know that when we have steady heat transfer by conduction, the rate of heat transfer is going to be the same. So P is equal to a constant. P is the rate of conduction heat transfer, and we have studied that in the lectures to be equal to Q over time. And it's also written as K1A delta T over L. So if this is constant, then it's the same across all of the slabs and at any location within the slabs as well. We know that what we want is T34, so I think it's convenient to study P4 and set this to be equal to some, I don't know, some known heat rate that we are studying. So we can either take, like I told you before, we can take the whole thing, P total, and we set these to be equal and solve. However, one issue in this situation, which will not really be very useful in solving the question, which is that if we want to study P total, which is all the way between these two ends, okay, delta T is known because I know T cold and T hot. However, because I don't know the thickness L2, then it's not really going to be easy to solve the question because I will have two unknowns. So let's try to solve on some layer that I know all of the quantities about it. And that's actually gonna be possible because I know T12. So since I have T12 here, then I'm going to study this layer. And rather than studying P total, I will just take T12. So in that case, I will get K4A delta T across layer 4 over L4 to be equal to, so basically we're studying from 1 to 2. This is layer 1, which has a thermal conductivity K1. The area is the same, and I have delta T1 over L1. So what we want is basically T34, right? And this will show up in delta T4, which is right here. So I'm going to just substitute for the quantity of interest. Of course, when we write delta T, remember, delta T is equal to T hot minus T cold, or whatever temperature is higher between the two temperatures that we have across a certain layer of interest. So for delta T4, which is across layer 4, I have T34 here and T4 here. But I know that T4 is T cold. So I will write here T34 first minus T4. So basically delta T4 is equal to the higher temperature minus the lower temperature. And we can see that T34 is greater than T4 since T4 is T cold. So we will have T34 minus T4 in our answer. And this is divided by the thickness of layer 4, which I have. And here I have K1A. Delta T1 is going to be, again, T higher minus T lower between the temperatures across layer 1. And across layer 1, I have T1, which is greater than T12. This is layer 1, and these are the temperatures at its ends. So I have T1 and T12, but T1 is T hot, so it represents the higher temperature across this layer. So delta T1 will be T1 minus T12. I will substitute this here. So again, what we want is T34. So I will simply just rearrange my equation. If you rearrange this, and by the way, you can see that A and A cancel out. So if you rearrange this, you should get K1 over K4 and L4 over L1 and T1 minus T12, all of that plus T4. So I just rearranged the equation for the quantity of interest. And if you look at our question, we have all of the unknowns in the equation. We have K1, it's 0.06, K4, which is 0.12. We have L4, 3.5, L1, 1.5. We have T1, 30 degrees, T12, 25 degrees, and T4, which is minus 10. I will leave things in centimeter because the units will cancel out. And the same thing for the temperature. I will leave it in degrees Celsius because we are studying the change in temperature here. So it doesn't matter if you put it in Kelvin or in Celsius, it's the same thing. And we will actually get a temperature of minus 4.2 degrees Celsius if we do the calculations. And of course, so basically we just got that this is minus 4.2 right here. And this makes sense because if the edge is at minus 10, then yeah, this might be some smaller negative quantity. Okay, so this was basically for this question. We found the interface temperature by studying the rate of heat transfer across the different layers. And knowing that we have a steady energy transfer, we equate the heat transfer rate across these different layers to find any quantity that we are interested in.